Welcome everyone. You are signed on to the Rotronic Instrument Corporation webinar, Uncertainty in Humidity Measurement. These webinars we put on, they're designed as educational webinars, and the purpose of them is threefold. Number one, we want you to make a better measurement, a more repeatable measurement, a more reliable measurement of humidity. And there's three steps to that. The first is to understand the parameter. We have a series of webinars on that. Second step is to understand the science behind the parameter. And the third is to understand the measurement process. And that's part of this course, is to understand the measurement process, which of course includes calibration and uncertainty. Everyone who registered for the webinar will get a copy of the slides and a link to the recording, and we provide that two ways. The first is with an email within about 24 hours of this live broadcast. Second way is we post it on the Rotronic.com website under the Measurement Academy section. Everyone signed on today is in a listen-only mode. That means you cannot speak to us directly with your computer or your phone, but we do want to hear from you. And the way to interact with us here is look at your control panel, the lower section there should be a questions pane. You can type in questions there, or you can type in comments there, and that's how we'd like to hear from you. There'll be two Q&A sessions during this webinar, one in the middle and one at the end. But as a question comes to mind, go ahead and just type it in, and we'll queue those up at those two Q&A sessions. So once again, this webinar is being recorded, and it will be available, the recording and the slides, to everybody who registered within about 24 hours of this broadcast. Okay, so this webinar is presented and produced by Rotronic Instrument Corporation. Rotronic offers NAVLAT, accredited calibrations for both humidity and temperature. And Rotronic also manufactures precision measurement instruments for, of course, humidity, dew point, carbon dioxide, temperature, water activity, and differential pressure. In addition to, we don't talk about the products during this webinar because it's strictly educational, but of course, if you have questions or you want to talk about products, we'd be delighted to hear from you. Just look up the contact page on the website and give us a call or find your local salesperson. Speaking today, my name is Bruce McDuffie. I'm with the Rotronic Marketing Department, and I've been in the humidity measurement business for about the past 10 years. Lots of strong application knowledge and humidity science and measurement knowledge. Michael Boetskis is your subject matter expert today. And Michael, he's the lead metrologist with the Rotronic Americas Group in relative humidity and temperature. Michael's been involved in manufacturing and calibration of both humidity and temperature instruments for about the past 19 years. Welcome, Michael.
Thanks, Bruce. It's great to be here today.
Thanks for helping me out with that acronym.
No worries.
And with that, let's, Michael, would you tell our audience what we'll be covering today?
Okay, Bruce. So today we're trying to do an introduction to uncertainty and uncertainty of measurement. We're not going to get too far into the details of it, but to give you an overview of what it is and how it applies to your instruments. So we'll start off with some terms and definitions to make sure that we're all on the same page about what we're talking about. Then we're going to move into understanding the uncertainty of your instrument. What do we need to consider and where do we get some of that information from? After that, we'll go into the calibration uncertainty and the uncertainty that we find on our calibration certificates. Hopefully most of you are getting certificates that are providing the uncertainty, and we'll talk about why it's important. Then we'll move into a slightly different topic, but ways for us to avoid out of tolerances on our instruments when they get sent in for calibration. And this in many ways relates directly to uncertainty analysis. And then as Bruce mentioned, we've got a couple places today where we've got questions and answers. There's actually two places, not just the one that we've got here listed. And that, Bruce, I believe we've got a poll to start off with.
Yeah, I think it's always interesting to see a little bit more information about the other folks out there listening. We've got about 100 people out there today. And these first couple of questions are to gauge the experience of our audience. And the first question is, What is your level of experience with uncertainty? Let's go ahead and choose one of those that you think is close enough to your current situation. And then after we get some results, I'll share it with the audience and we can see level of knowledge out there. Looks like it's a pretty good mix so far. Are you an expert? Are you a professional metrologist? I suppose you could argue those are the same, but we put them in there anyways. Are you a novice? You know enough to get your job done, or you're not certain? Anytime we do an uncertainty webinar, we got to get that joke out of the way early.
We try to put it in there only once, but
And I'll try not to use it again.
no promises.
Yeah, I can't promise it. All right, thanks everyone. I'll close the poll and we'll share the results. And you can see most folks know enough about it to get the job done. Pretty good mix. A few experts out there. Good. And I've got one more slide here to ask about your expertise in humidity. A minute to launch it here. Here we go. What is your level of experience with humidity measurement? Once again, are you an expert, a novice, enough to get the job done, or somewhere in between novice and expert? This helps us to gauge the presentation a little bit. But mostly I think it's interesting to see the cross-section out there in the audience. And we've got a couple of other polls. I think we've got 3 other polls interspersed throughout the presentation with some other interesting questions. Go ahead, give it a couple more seconds. Looks like most folks have voted who want to. Close the poll. I'll share the results. And once again, we can see we have most folks enough to get the job done. Okay. Thank you for sharing that information. And with that, we're going to go ahead and move along into the presentation. First section is talking about terms and definitions. And this one might seem extremely basic, but I think it's important to level set here. And a measurement itself is something we do to determine a property. And it could tell us, for example, how heavy an object is, how hot it is, how long it is, or in this case, how much water vapor is present. And they're always made using some type of instrument. For example, relative humidity, we'll use a hygrometer. And it could be any type of measurement instrument. And the result is normally in 2 parts. It's usually a number and a unit of measurement. But the fact is, as we know in metrology, there's no such thing as a true or a perfect measurement. Thus, this is where uncertainty comes in, because it tells us the fitness of the measurement. And a true proper measurement is only complete if it has that statement of uncertainty with it. And that's what we're going to talk about today. When we know the uncertainty, the benefit is that it helps us determine the fitness of the measurement, or how good the measurement is in accomplishing what we want it to do in this measurement case. And also, if we understand uncertainty, we can start to reduce it. And with that, let's clear up a few other terms here that we should address briefly. And the first one is accuracy. Michael, tell us about accuracy.
So accuracy, and this is a definition that I've taken from the VIM, which in the metrology world is essentially our primary dictionary. And it defines accuracy as the closeness of agreement between a measured quantity value and a true quantity value of a measure end. And our measure end, that's just what we are trying to measure, be it the amount of humidity in the air, the length of a gauge block, something like that. Now, so this is a fairly simple definition. We're just looking at the difference between 2 things. But as Bruce just explained, we never know the true value of a parameter or an item. We're always making an estimate of it. So we can right away see the limitations of accuracy because it's assuming that what we're comparing against is a perfect value. So again, accuracy, it's just that closeness of agreement between those 2 figures. Bruce, maybe you can take us through error then.
Yeah, error is I like to call it the opposite of accuracy. Accuracy is the closeness, error is the difference. And again, it's a qualitative term. It is not a quantitative term. And I think that's the takeaway from these definitions is to quantify a measurement, you use uncertainty. For a qualitative statement, you can use accuracy or error. But let's talk about Michael, the definition of uncertainty, the term.
Okay, so again, a few more definitions here, where uncertainty is the quantification of the doubt about the measurement result. So we know with every measurement result, there's some uncertainty in it, and that's not to say that we're not confident in our measurement instrument. It's just a reflection that there are many different influences on the environment and on our instrument that can change or have an effect on our actual measurement. So at the bottom here, I've got an example of what a measurement could look like. We've got it as 50% relative humidity, so our actual measured value, plus or minus 1% RH. That 1% is our uncertainty value. And then I've got a K equals 2. And essentially with uncertainty, we also have an uncertainty in our uncertainty. The K equals 2 is indicating the confidence level that we've got in it. And in this case, when K equals 2, that gives us about a 95% confidence level. Another way of looking at this that most people are maybe a little bit more familiar with is political polls or other sampling like that, where a report might be one party has support from 40% of the population with an error of plus or minus 2%, 19 times out of 20. That 19 times out of 20 is the same thing here as our confidence level. And in that case as well, we see it's 95%. Most times when we're reporting values, you see it reported at the 95%, but occasionally it comes out as 99% as well. And we'll see a few examples later on of how that can come into play.
Good. Well, let's get and put it into the world of our audience, Michael. Let's talk about understanding the uncertainty of the humidity instrument itself that's used from a day-to-day basis.
Okay. To start with any calculation of uncertainty, we need to look for the different contributors. What things can contribute to our overall uncertainty? And we need to come up with an overall list of these, and then later on we go and combine these together. So of the things that can create or add uncertainty to our measurement, we have things like the instrument calibration, we have resolution of the instrument, long-term drift. Depending on where an instrument is being used, it can see greater drift. Temperature effects, the electronics in an instrument may be sensitive to temperature, or perhaps a sensor is sensitive to temperature, and there might be a temperature component in our measurement. Potentially hysteresis, so if we're approaching a measurement point from below or above, we might get slightly different readings. Linearity of the instrument may come into play, and quite often linearity gets included in an accuracy specification. So a manufacturer will say, well, an instrument has an accuracy of 0.8%, and all that's saying is it's limiting the error between the reference and the instrument to that 0.8%. So essentially our linearity over all points is that. We might have some other sensitivity to contamination. This list is not necessarily complete for all instrument types or all environments. You need to take a look at what's present, what sensitivities the particular instrument type that you're using has, and come up with as good a list as possible. Now, just to try to take this to a relatively simple example, we'll take a look at just a standard humidity, handheld humidity instrument and look at what the overall uncertainty of that instrument would be for how most people would end up using it. In this case, I'm assuming that we don't have any environmental factors that are coming into play. We're primarily looking at the original calibration, the performance of the instrument itself, as well as what the annual drift of the instrument is. All of these values actually end up coming from typically spec sheets and the original calibration certificate. So what I've done here is I've created what's called an uncertainty budget, and this is how we document all the sources of uncertainty that we want to include and combine those together. So to start off with, we've got the uncertainty contributors. In this case, I've determined that we're dealing with accuracy, calibration uncertainty, and our annual drift. And I've just taken these values from data sheets or from the calibration certificate that I got with this instrument. So we're dealing with 0.8% RH for accuracy. The uncertainty on our calibration certificate listed it as 0.5% RH, and the manufacturer tolerance for annual drift says it's better than 1%, but since I don't know for this particular instrument what it's going to be, my best estimate right now is 1%. Perhaps in the future, after I have some calibration cycles under my belt, I can look at lowering that or potentially raising it depending on my environment. We don't just then add these together in a standard way, just summing them all up. That would give us quite a large uncertainty, and that's not truly reflective of the performance of the instrument. What we do is we've defined these expanded uncertainty values. We take them down to a standard uncertainty. Each of these uncertainties might have a different distribution, be it rectangular or a normal distribution for how we expect the values to land. And there's some predefined divisors to create our standard uncertainty. So we've gone and done that, and then we use the formula listed here to combine those all together. So for the standard uncertainties, we are taking the root of the sum of the squares of all those values to get our combined uncertainty, and then we multiply that by our confidence factor or our coverage factor to get, in this case, an overall uncertainty of 1.6%. Now, I had mentioned that we can use different levels of confidence in our uncertainty budgets, and this chart here gives you an idea of how much confidence you can have with the different coverage factors. So our combined uncertainty, for example, would have a coverage factor of 1. So in that, we'd expect it to have a confidence level of about 68%, which isn't particularly great. That for a given measurement, we would be confident that the best estimate of that value is within within this combined uncertainty value. Typically, most laboratories use K equals 2 and state that they've got a level of confidence of about 95%. 95%. Truly, it's 95.45, but just to keep everything simple, we typically use a coverage factor of 2 and say 95%. Now, this uncertainty can have has a pretty big impact on how we use the instrument and how and the performance that we can say that instrument has. It's important for us to remember that each instrument is unique in behavior. This comes down to some essentially manufacturing difference in individual components, but it also really comes down to the environmental factors. What has a particular instrument been exposed to, and can that affect how that instrument performs? It's also very important for us to understand the impact of calibration. We saw that the calibration uncertainty is included in the uncertainty budget. So as that calibration uncertainty changes, so does the overall performance of our instrument. If one calibration calibration has an uncertainty of 0.5% RH and another has an uncertainty of 2% RH, you can see that the instrument performance will change quite significantly. And I believe with that, we go into another poll.
We do have another poll. And the question here, I'll have to get it so I can share it. We'd like to know, what's your biggest challenge with it when it comes to humidity and uncertainty? And you can choose more than one here. They could all be challenges for you. Go ahead and choose the ones that apply to you. Is it understanding why you should care about uncertainty? Is it that your humidity measurements are unreliable? Is it that your humidity measurements just are not consistent? You just don't understand uncertainty? Or is it something else? And if it's something else, you feel free to type it into the question pane, and I can share that with the audience too. And by the way, after this poll, we will have a Q&A session. So type in your questions and we'll make sure we address those with Michael, our subject matter expert. By the way, we have a surprise guest that showed up today from Rotronic. We've got David Love, the managing director of the Rotronic Americas, is here joining us as well.
Well, thanks, Bruce. I had to unmute myself there for a second. I want to welcome everybody to our webinar, and please encourage you to reach out to Bruce and Michael or myself or any of our regional salespeople for any questions or issues you may have about this webinar. And we're always available to come visit your factory. Thank you, Bruce.
Thanks, David. We don't let David talk too much on these webinars, but once in a while we have him on for a guest. Okay, I'm going to close the poll and share the results. Looks like humidity measurements are not consistent. Michael, that's the biggest challenge.
And I believe that's something we hear a lot,
Yeah.
and I think a lot of it comes down to understanding the total performance of an instrument. And I truly find it amazing sometimes. It's a pretty widespread misunderstanding of the instrument performance. So hopefully we can help you out with that today.
Yeah, we're going to cover that here in a little bit. We had one James typed in the question pane. He said, the challenge is understanding how does uncertainty affect my in-house calibrations? It's a good one.
Well, uncertainty affects every measurement. So when you're doing an in-house calibration or sending a unit out for calibration, it's important to understand what the uncertainty is of the reference equipment, for example. If not knowing how, James, your in-house calibration is working, if the in-house calibration lab has very high uncertainties, they might not be able to transfer over or calibrate your instrument to the point where it's meeting manufacturer specification. So there's a lot of things going on there. Based on that question, it's a little hard to say how it might come into play, but essentially every calibration has an uncertainty. If the uncertainties are not being reported, you don't really know how good of a calibration it is or whether or not your instrument is going to perform the way that you want it to. So very important to understand that, understand the uncertainties of the calibration and what's going on for it.
Okay, here's a question, Michael, from Craig. He says, increasing our lab capability, oh, these are challenges, sorry. Increasing our lab capability and trying to get a handle on sources of uncertainty. And Daniel had a clarification. He was asking, so the lower the K, the higher the confidence. Actually, it's the opposite. The higher the K, the better the confidence. Isn't that right?
That's correct. The K value of 1, for example, just gave 68% confidence. K value of 2 gave us about 95. When we're getting up into the 2.5 and 3 K values, then we're getting into the 99% confidence levels. So the higher the K value, and remember that K value is used to multiply the combined uncertainty to create our expanded uncertainty. So the higher the K value, the higher the expanded uncertainty value gets to be. And of course, if that expanded uncertainty was infinitely large, your confidence level would be 100% because you know everything is within that. It's only as that becomes smaller and smaller that we start to introduce the risk that we haven't covered. Our uncertainty doesn't cover where the measurement actually is.
Here's a question from George. His question is, does the data refresh rate or the response time affect uncertainty?
It can affect uncertainty, especially if you've got a very fast moving environment. Potentially your instrument is not sampling fast enough to get all the peaks and valleys that are coming in. So it can absolutely have an impact on your uncertainty, especially if you're trying to take an average over a long period of time. Your refresh rate needs to be adequate to actually see what's going on.
And here's last question before we move on to the next part of the presentation. It's from Frank. He says, how do I know my 1+ year-old sensor is still accurate?
It's a very good question, and one that comes up a lot. Really, Frank, the only way you know that your 1 year old or longer aged sensor, and from that I'm assuming he means 1 year from its last calibration date. But the only way to know that it's still accurate is to get it calibrated again. You need to, it needs to be compared against a known reference or a well-estimated reference to ensure that it hasn't seen a significant amount of drift and that it's still operating within the expected parameters.
Okay. And one last quick one I want to get in here from Zachary. I think this is a follow-up to your last answer. What would be considered a fast-moving environment?
Well, that's going to change depending on what your sample rate is. Some examples of fast-moving environments could be a chamber with a controlled temperature. Those can move very quickly, and they will cycle. The chamber is going to cycle heating and cooling depending on what the set point is and how much temperature leakage outside of the chamber there is. And so there will be an oscillation, and the question is how fast is that oscillation compared to the sample rate of the instrument.
Good questions, folks. Thanks for typing those in. And we've got another Q&A session at the end of the webinar. So again, as something comes to mind, go ahead and type your question in there and we'll address it. If we don't have time at the end to address all the questions, we'll be sure to get back to you via email. So with that, Michael, let's talk about specifically the calibration certificate and uncertainty, how that applies there.
Okay, so for this, what I've done is I've created two uncertainty budgets that we're going to take a look at and look at the difference between two calibration setups. Both of them are humidity calibration setups using a divided flow system, which is fairly common for humidity calibrations. But we're looking at two setups. One is using a chilled mirror as the reference instrument, and the other one is using the internal control probe as the reference. Both are completely valid ways of using these divided flow systems for calibrations, but we just want to look at what the difference is in overall uncertainty to see how that impacts our instruments. And hopefully that will get you thinking a little bit more about how your calibration provider calibrates your instruments and understanding why that's an important parameter for you to look at, both when selecting a vendor and for determining whether or not your instrument's in tolerance or working the way you expect it to be. So I won't go too in depth in these budgets, but I've just created a simple budget for this humidity calibration. You can see here we've got our chilled mirror uncertainties. If we've got a chilled mirror, in order to convert dew point or frost point to relative humidity, We also need to know our temperature value, so we have to include the uncertainty of our temperature probes. And then we've got other uncertainties related to the chamber, related to temperature gradients within that chamber, stability of the temperature, stability of the humidity. So these are all different parameters that come into play, and we need to take into account when we're doing a humidity calibration. A lot of these apply not only to calibration, but also on a larger scale to when we're actually making a measurement out in the field with our handheld. If we're trying to measure the humidity of a large room, for example, and we go in with one sensor, we'll know the humidity at that point, but the humidity in that room may vary just as there's temperature gradients across the room, there's hot spots, cold spots. The relative humidity in those areas will change. So while we look at this very closely in calibration, it does also apply when you're making measurements out in the field. So we've got the chilled mirror, we've got all our other uncertainties here. This budget's slightly more complex than the example we showed before because some of our units now are in degrees C, not relative humidity. So we've got a sensitivity coefficient that allows us to convert the impact of this uncertainty in degrees C into % relative humidity. And this is something that was calculated beforehand. So with this, once we go through all our calculations and come up with our expanded uncertainty, we're left with an uncertainty of 0.7% RH at the 95% confidence level. This is quite a good uncertainty for a humidity calibration. Depending on the lab, sometimes this can get improved slightly, but for a divided flow system, this is actually a very good expanded uncertainty. And I'll point out that this is at 80% RH at 23C. That does have an impact on this uncertainty. At lower humidities, this uncertainty value is actually lower. But so with this system, this setup, chilled mirror, we're able to get this 0.7% RH uncertainty. If we take this exact same setup, but we don't use the chilled mirror for our reference, we end up with a slightly different uncertainty. Our contributors are now different. We're now looking at the reference probe itself. In this case, we've got an uncertainty for that of 1.1%. Once we look at the drift of the reference probe, we've got this, again, it's a new unit, so all we can go with is the manufacturer specification of better than 1%. So we've done a worst case estimate here of the 1% for the drift. But most of the rest of the items, they're exactly the same as what we had before. But now when we look at the expanded uncertainty, instead of having a 0.7% uncertainty, the uncertainty is now ballooned up to 1.7%. So just by changing that piece of reference equipment, with everything else remaining the same, our expanded uncertainty has grown by 1%. Now, I've just used a real simple example here of a chilled mirror versus the internal sensor. There are ways to make both of these slightly better. For example, if this probe was calibrated on a regular basis, maybe less than 1 year, we could reduce things like the drift value. We could start to measure what the drift is from between calibrations and lower that. If we were able to get it calibrated a little bit better or reduce some of the error limits on it, we could reduce some of these values. Same for the chilled mirror. The previous example had a very specific chilled mirror. A different chilled mirror might give us different uncertainty values. So it's important for us to know what the reference is and what the uncertainty of that reference is, because it does make a significant difference in what our overall expanded uncertainty is for the calibration. Now, why is this important? Well, let's take a look then at what the impact is on the instrument that we're calibrating. If we go and take the example of the instrument I showed earlier on and just change the calibration uncertainty values for those two calibrations that we just looked at, so the divided flow with a chilled mirror or the divided flow with an internal probe. So all we've done now is change these uncertainty values, but now the overall performance of our instrument, or the expanded uncertainty of the instrument's measurements, they're quite different. The calibration with the chilled mirror, we now have an uncertainty of 1.7% RH. If we just were using that control sensor as it was, we're left with an uncertainty of a 2.3% RH instrument at the end of it. So the calibration uncertainty ends up having a big impact in the overall performance of an instrument. So if you're looking to get your instrument calibrated and back to factory specification, it's important that the uncertainty of your calibration is the same or better than what the uncertainty at the factory was. And this is one of the things that comes into play a lot when people are talking about their humidity measurements not being reliable, or talking about having issues with their humidity instruments being out of tolerance on a regular basis. Quite often, people are not looking at what the calibration uncertainty is and what impact that has on the overall instrument performance. So another way that the uncertainty is important is technically it is required to have proper traceability. Traceability is more than just having a measurement that gets linked back to NIST. It's actually knowing what the uncertainty is along every step of that chain. Without the uncertainty being known, traceability really doesn't mean much, because what's trying to be portrayed there is that you're getting a good measurement, or you know the uncertainty of your measurement, how close of agreement you've got with NIST. It's not good enough just to have that chain. You want to know how the uncertainty grows over time. This uncertainty on the calibration certificate also gives you a good insight into the overall quality of the calibration. If you've got a very tight uncertainty on your certificate, that's indicating that the lab is doing a lot to reduce their uncertainties and control everything as much as possible, and that's going to give you a better performing instrument at the end. If the uncertainties are very large, they could even be larger than what you're trying to measure with your instrument, especially if you've got a unit that you're trying to get measurements at the 1.5% level for. If you're starting with an uncertainty of 2%, for example, that's not an adequate calibration for your instrument. So very important for us to take this into account, and it can really make the difference between an instrument meeting manufacturer specification or just being out of tolerance. So very important for us to look at.
And Michael, a couple of things on these topics, folks. We have two great on-demand webinars. One is Interpreting Humidity Instrument Specifications, which is the whole hour webinar all about this topic. And there's another webinar on demand for traceability, what it is and how to get it. And they're both on-demand webinars. You can look at them. Just go to the Rotronic.com website, look for Measurement Academy, and they're all listed there, including the slide decks. And also, one more thing, I didn't mention this earlier, but if you look in your control panel, there's a section that says handouts, and there's 4 great references that go into more detail about uncertainty and accuracy demystified, and even the capacitive humidity sensor. You can just download any of those or all of them directly from your control panel. Okay, just wanted to get that out there. Michael, back to you.
Thanks, Bruce. Another place where uncertainty can be important is when we're looking at our pass-fail criteria, and whether an instrument is passing the calibration or essentially in tolerance or out of tolerance. And this is a relatively new topic that's, for accredited labs at least, starting to become a little bit more important, and we're going to see it a little bit more, especially as the new version of the ISO 17025 comes out later this year. And to look, I just wanted to start with us thinking about what our potential, what sort of results we can see from a calibration, and how they're either in pass or fail mode. So in this diagram here, we've essentially got an example of a test point. We've got a nominal value, let's call it 50%, and then we've got a series of measurements that an instrument might make. So those are represented just by these points here. These are the actual measurements that an instrument might have. The error bars that we're showing on these points are actually uncertainty bars. They're representing the uncertainty of the measurement. And so we just want to look at what happens as that measurement point approaches our specification limits. You can see in these first two examples, it's pretty simple. Even the uncertainty bars are within the specification limits. Pretty easy to say that these are pass. The challenge gets to be when the uncertainty value crosses over the specification limit. There's always a chance now, or there's a risk now, that even though the measured value is less than the specification limit or within the specification limits, there is a risk that this unit is actually out of tolerance. The same actually applies in the other way for these values, or for not the last value, but these other two, that even though the point is out of tolerance, once we take into account the uncertainty, well, maybe we are actually in tolerance. So there is some statistical probability of this. And one of the questions that's been going around more and more now is, how do we take that risk into account? How do we make a better estimate of, or better statement of pass or fail? And one way that's been described, and it's actually to limit the risk of the false accept. So limit the risk that one of these points where the actual measured value is within tolerance, limit the risk that it's actually out of tolerance. And through some formulas, what we can do is create a guard band limit where we limit the risk of a false accept to 2%. And what that does is it says that as long as our measured value is within the new guard band limit, then we can call it a pass. And the risk of it being actually out of tolerance is only 2%. The example here where we're across that guard band limit, we would then call it an indeterminate. That just means that the lab can't state with less than 2% risk that it is actually in tolerance. That doesn't mean that the end user needs to say it's out of tolerance. That's up to the end user to make that determination, but then they're accepting the greater risk that it is actually out of tolerance. Typically, as soon as the measured value goes outside of the upper specification limit, typically we're still going to call those a fail, just because the probability of them being intolerance goes down significantly. So the risk of them being them intolerance, even though we're calling them out of tolerance, is pretty small. And most of us want to err on the side of caution for that. So now we end up with, instead of just pass fail, we end up with the case where we can have a pass result, a fail result, or an indeterminate result. So you're probably going to start to see these on more and more calibration certificates. You won't see indeterminate unless you've got a value that's crossing this guard band level. But especially once the new ISO 17025 comes out later this year, more and more labs are going to start to report the values in this format. So it's just something for you to understand, and hopefully not to be too surprised of when it comes out. Bruce, I believe we've got another poll then to go into.
We do. This poll is about how you deal, how you interpret your calibration cert. And the question is, see if it launches here. There we go. Have you ever looked at the uncertainty statement on your calibration certificate? Yes, you have. No, you haven't. Or maybe you've looked for it but couldn't find it. We'll leave it up for a few seconds here. And I think, Michael, if they look for it and can't find it, that probably means it's not an accredited calibration. Is that true?
Quite often that is very true. Most times, or for a large percentage of labs, they don't report uncertainty on the non-accredited calibrations. In order to get the uncertainty statement there, you need to move up into their accredited calibration offering. So that's, if it's not there, it's typically just the non-accredited calibration.
Okay, thanks. It looks like everyone's voted. I'll close the poll and share the results. Interesting. About 60% have looked for it and found it. Some have not, and some looked for it but couldn't find it.
That's great to see that majority of people have looked for it and are looking at that. That's great.
Okay, and folks, keep those questions coming in. I see a lot of good ones queued up there for the next Q&A session. And just before that, we have one last section to cover, and that is how to avoid that dreaded out of tolerance. Michael?
Okay. So, go back to the right page there. So, to avoid an out of tolerance, we need to know what's causing the out of tolerance. The better we can understand that, the better we can implement actions to reduce the risk of it. Quite often, an out of tolerance is due to the instrument or sensor drift. One of the realities with any measurement instrument is there's drift in them. Technologies are getting better, that drift is coming down, but there is still drift in every measurement instrument. Another cause of an out of tolerance could be potentially using an incorrect acceptance criteria, or maybe too tight of an acceptance criteria. If you're just using the accuracy specification, which doesn't take into account, for example, the calibration uncertainty of the reference instrument, you're potentially applying too strict of a standard onto your measurement instrument, and that can create out of tolerances when there isn't necessarily one. Maybe the previous calibration was not suitable. Maybe the uncertainties for that calibration were very large, and then if you combine that with a tighter specification limit, that can create year to year. Your instrument might not be drifting, but the reference point at the calibration site is, and your instrument may end up being more stable than theirs. And if your accuracy specification or your acceptance limit is too tight, you might just see a out of tolerance solely because the calibration is not suitable for what you're trying to do. Typically, the cause of an out of tolerance can be traced back to an error in an uncertainty budget or a lack of uncertainty analysis for a particular instrument. So an error might be just that you didn't know about a contaminant or an uncertainty component that will affect your instrument. It could be something that you learn over time. So it's important to look at those and keep looking at them and reviewing them over time. So to avoid the out of tolerance situations, it's important to know the sensitivities of the instrument and where it's being used. Is there something here that's going to affect my instrument, and do I need to either shorten my calibration cycle, or do I need to increase my acceptance limits to account for whatever environment I'm going into? It's important to include the long-term drift in your acceptance limits. know what the manufacturer says this instrument will stay within. And that can be going farther than just looking at the accuracy spec. For many instruments, you need to look at what the long-term drift is as well. And then the final one is to ensure you've got an appropriate calibration provider and that they're providing suitable calibration uncertainties. Those uncertainties do impact what the overall performance of the instrument is, and if you don't have a suitable calibration vendor, or you don't know what their uncertainties are, you really don't know what the performance of the instrument is. You can't properly assign tolerance limits for the next calibration. So those are some key things that will help you avoid out of tolerance situations. Bruce, I'll pass it over to you then.
Yeah, we have one last poll. I'd like to get some feedback from the audience on this one, and this is regarding out of tolerance. And the question is, what action do you take for an out of a tolerance calibration result? And you can select more than one on this list. You ignore it and continue to use the instrument? Do you take corrective action in accordance with your process? You've never had it happen, or you adjust the calibration interval, or you change the tolerance in your documentation and standards. See what kind of action folks are taking. Looks like most folks are taking corrective action in accordance with the process. That's probably the best answer, isn't it, Michael?
It truly is. It can lead to a whole bunch of different things that corrective action will cause you to do, including things like potentially adjusting calibration interval or changing tolerance. So possibly those are where we got people selecting both. Glad to see so far we don't have anyone ignoring it.
I thought we'd get a few of those. Maybe people are afraid to say it.
Possibly.
Okay, I think that's good. Looks like a few more folks are voting. Last chance. Go ahead and close the poll, and I'll share the results. And there everyone can see it. Some folks adjust the calibration interval. A little of everything except ignoring it. That's good. That's good news.
Great to hear.
Okay, well, let's go ahead and Michael will share the high points, the last points that you should really take away from this, or the high points you should take away from this webinar. And then don't go anywhere because we have a final Q&A session. We'll have some time to take some more questions. So Michael, let's talk about the high points.
Okay, so one of the key things that hopefully we've gotten across today is that instrument performance is more than just an accuracy specification from a data sheet. Sometimes that will cover the complete uncertainty, but more often than not, there's other components that you need to take into account when looking at the total performance of your instrument, especially a year from now, assuming you've got a 1-year calibration interval. Two instruments, even of the same model, can have different measurement uncertainties, potentially if they're being used in different environments, or if they've got different calibration vendors, they can have different measurement uncertainties and different overall performance. If we want to get in and really start to reduce our out of tolerances, the more we can understand about the instrument, how it behaves, and the different uncertainty components that it has, the better we're able to limit the risk of an out of tolerance. There's always going to be some risk of it, but the more that we know about it and the uncertainty sources, and the better we can estimate those, the better chance we have of reducing the risk of out of tolerance. And with that, Bruce, what do we have in the way of questions? Bruce, I think you might have muted yourself there.
Sorry about that, Michael. A lot of chatter around my office today, so apologize for that and trying to keep it nice and quiet. Question from Brian. Brian says, what range do you consider good temperature stability before recording a temperature and RH value? And then he says, that is, when do we know a sample is stable enough to record an accurate value?
That's a very good question. It comes down to what you need out of your uncertainties. The temperature stability will affect the uncertainty of your measurement. So you need to look at what is my required uncertainty for this calibration point, and from that, look at what you need from your temperature stability. If you don't need something particularly accurate, you might need it. You might be able to have it. That doesn't need to be as stable. But if you're looking to get as good a calibration as possible, you want to make it as stable as possible, especially if you've got other contributing factors that are quite large. So unfortunately, there's no single answer to that. It depends on what you're trying to get out of the calibration, and you just need to adjust your acceptance criteria based on that.
Okay, here's a question from Eduardo. He says, how can we consider the temperature sensitivity value if this is not given by the manufacturer of the instrument under calibration?
I'm assuming here you're talking about the temperature sensitivity of the instrument itself and how it performs over at different temperatures, rather than
I think he was referring to your uncertainty budget where you talked about temperature sensitivity with BC, I believe.
Okay, well, within the uncertainty budget, essentially what you need to do there is find a good humidity calculator, and there is one available on the Rotronic website. And in there, you can calculate out what the temperature sensitivity value is. It changes for every humidity and even over temperatures, it will potentially change slightly. So it's something that you need to calculate out for each test point that you've got. It's not something that a manufacturer would specify because it's not instrument specific. It's actually going back to the fundamentals of humidity and understanding relative humidity and how temperature affects it.
Okay, and this is a question in reference to your out of tolerance slide, Michael. And why is the third point considered a pass if the uncertainty is outside of the upper specification limit?
Okay, that one is considered a pass. I'll put a caveat on that. It's still considered a pass, and that's because the measured value of the instrument was less than the guard band limit. So in that case, it's considered a pass with a less than 2% risk that it's a false accept, so that it's actually a fail. So it is considered a pass. There is a 2% risk in that case that it is actually out of tolerance. And part of the reason for having this in here is, especially when it comes to humidity instruments, the ratio of the calibration uncertainty to the uncertainty of the overall instrument gets to be quite low. Historically, going back many decades, there was something called the test accuracy ratio, and you wanted to calibrate an instrument with something else that was 10 times more accurate. As instruments have improved, that ratio was kept going down, and today a general rule of thumb is a 4-to-1 ratio. With humidity instruments, quite often it's even less than this, a 1-to-1 or a 2-to-1 ratio. And if we called everything out of tolerance, even if the uncertainty band went over our acceptance limit, we'd be able to accept almost nothing as intolerance. And this isn't unique just to humidity instruments. This applies across the board for all measurement instruments. So we've had to come up with statistical methods to quantify the risk associated with it, so that we can provide good instruments and low uncertainty instruments to customers, and still be able to calibrate them with available systems out there. So that's why it's still a pass. There is a risk associated with it, but it still counts as a pass.
And that's about all the time we have, folks. And So we're going to go ahead and wrap it up. We've got a couple of more slides. I think David Love wanted to say one last thing before we signed off. David?
Well, Bruce, I appreciate you letting me talk, since you tend to keep me muted all the time. I'm not quite sure why you don't want me to talk. Maybe it's because that I might say something that is in disagreement with what you guys have said. But today I don't, you guys have done an absolute fantastic job presenting uncertainty. And for everybody out there who's scratching their head a little bit, trying to say, why can't I figure out uncertainty? Well, Bruce, myself, and Michael, we have been in this business for more than 15 years, all of us. We've been addressing this uncertainty issue for more than 15 years, and we still sometimes scratch our head, not trying to be able to completely understand what's going on. Uncertainty and guard banding and the issues that are coming out of the new ISO 17025 standards are going to make the issue of pass-fail, the issue of out of tolerance, become more and more complicated. And I just wanted to put out to everybody on this webinar that we are somewhat on the leading edge, right, Michael, in terms of guard banding and dealing with the new ISO standards. We had to deal with this last winter. And so if you're looking for some help, Mike Botsky's is a great resource, Bruce, myself, or any of our technical salespeople that are out in the field, please give us a call. You don't even need to be buying something. We just want to help you guys be able to, avoid that dreaded out of tolerance, avoid that audit that is just going to keep you away from your family on weekends. So we're here to help. We're here to try to educate everyone because this is an ongoing process. And Bruce and Michael, thank you very much for another excellent webinar. And I would encourage everyone on the conference to visit our website and take a look at all the other webinars that Bruce and Mike have put together. There's some really good stuff out there. Thanks, guys.
Thanks, David. And folks, if you want more, download those assets from the handouts section. I'll leave that up for a few minutes here. And check out the Rotronic Measurement Academy. There's great humidity resources. There's psychrometric charts, technical notes, humidity calculator, all kinds of fun humidity stuff. Next webinar will be about dew point temperature in compressed air, October 19th at 1 p.m. Eastern. Be sure to sign up for that one especially if you're running a compressed air system. Or if you didn't have enough fun with humidity on this webinar, this one's guaranteed to be even more fun. Please give us your feedback on the webinar survey. Should pop up when you close out. We want these to be useful. We want you to be able to use this information to make your lives, day-to-day lives and struggles with humidity easier. And thank you everyone for taking the time out to attend the webinar, this live webinar today. Everybody will get a copy of the slides and a link to the live recording tomorrow via email. Thank you, Michael. Very informative. I learned a lot. I think our audience did too.
Thank you, Bruce, and thank you all for joining us.